Welcome back from coffee. Let's start with Prabhakar Palani from IIT Mandi, and he will talk about jets and heavy flavor production at the EIC. Please.
Okay, thank you. So first of all, I would like to thank organizers to giving me opportunity to talk about the jets and the heavy flavor. And there is a disclaimer. So I'm going to show the results which are not mine. So I will give the broad overview of the jets and the heavy flavor physics that can be done at EIC and the recent development in this jet physics related to the EIC. And secondly, I'm an experimentalist, so I'm going to give an overview from my experimentalist perspective. Okay, so it is a bit different. Okay, I will not go into the detail of each topic, but I will just give the overview of the observables or results. Okay. Yes, so jets are important to study at EIC, and you can see over here. Before LO report, there was very few studies mentioned in the EIC physics, but you can see these processes, different processes, and these are the topics they have included in this EIC physics. And in yellow report, you can see that jets are included and the dijets and the heavy quark related studies. So this black one is the observables or the studies that have been included in this LO report. So it is important to study the jets and the heavy flavor at EIC. What are jets? I think everyone know here. So let me briefly go through that. So it is a proxy for quark or gluon, which fragments, and then it hadronizes non-perturbatively, and we see those hadrons in our detector. So this is the dijet event in Atlas, which you can see. And since at EIC we are going to study these TMDs and GPDs and all, which is trying to probe quarks and gluons, it is very important to know the dynamics of quarks and gluons in the precise or more better way. So I'm going to focus on few processes, and here are some of the Feynman diagram for those processes. For example, I'll be talking about the dijets, or here the different diffractive digest photoproduction, or the direct process is given, and this is right hand side is the process for the resolve case where this photon is having this hadronic contribution, and then it produces these dijets. Along with this, I'll be mainly talking about photon-gluon fusion and also the QCD Compton scattering processes. And of course, I will talk about the leading order deep inelastic scattering. Okay, so over the years in the past, HERA has given us nice measurements related to the jets, and you can see here the normalized cross-section for jets as a function of PT for various virtuality bins going from 5.5 GeV to up to 15,000 GeV square. And these measurements are also compared with the NNLO calculations, and you can see they are also doing a pretty good job in explaining the data. So if you put that and try to measure this alpha S as a function of this energy scale, then you can see that it nicely fits into this volt average, and you can see measurements from H1 and the Zuis for the inclusive jets, and also there are the measurements for the port jets and the other calculation from the CMS. And we can use this precise jet measurement to constrain our PDF and moreover, we can extract the alpha S with better precision. So moving from H1 to EIC, we can further improve our calculations, and that will help us to constrain the PDF and also the alpha S in future. Okay. So now let me go to the next leading order deep inelastic scattering process. So I'll be talking about this process and the jet which we get as a precision tool in electron-ion EA collision, for example. So you can consider this process where we have this electron which we use as a tag, and the other quark which gives the jet as a probe, and then we try to study this kind of process in this EA collision. So we analyze the propagation of this quark through this nucleus and other structure or other among the other nucleons, and how it hadronizes and all. So we can use this jet as a precision tool in this case. But there are some challenges. We have to precisely match this stuck quark jet by separating the beam remnant that comes out of this process. So I will show one of the results where people try to separate this beam remnant from the other stuck quark. So this is the work, I think, from Felix Young. So where you can see this is the polar form of the electrons and the stuck quark, which is shown in this plot, where you have this momentum going from the center of this axis, and you have this eta region. So on top half of this you have the electrons, and the bottom half you have the stuck quark. And this is for the low q square, but if you go to the high q square region, you can nicely separate this electron and the stuck quark jet. You can do things better. You can put additional requirement on this back-to-back going object, electron and quark, where you put this delta phi cut, which is less than 0.4, and you try to separate this remnant part. So in this way, you can have this tag electron which is going in this direction. You have this opposite side going remnant, which is this, and then you have this jet. Okay, so this is the jet, and this is the remnant part, or you can see in this diagram. So once we precisely try to separate this quark as well as electron and measure them, we can go and do our next studies. So this is one of the work where they try to measure this PT broadening in case of this EA collision. So this is the lepton and jet azimuthal correlation, where this black line corresponds to the EP case. And if you go and add this Q hat L, which corresponds to the transverse momentum gained by the quark when it travels through this nucleus, it experiences the multiple interactions, and that give rise to the PT broadening. And you can see that this blue dotted curve, which is having slightly a broader shape, and then if you go to the higher Q hat, you have a larger broadening. So this study using this jet from this leading order DIS, you can use that as a clean channel to measure the jet transport parameter, Q hat, and the nuclear quark TMD PDF distributions. Okay. So before going to the jet substructure measurements, I would like to briefly go through the terminology that we use. So jet substructure observable or jet substructure is one of the novel probe to study the nuclear effects at future EIC. So we try to use the soft drop groom jet to do the grooming, and we use this angularly ordered Cambridge-Achen reclustering of jets, and then we try to get the groom jet. So you can see this ZG, which is the ratio of subleading to the sum of the subleading plus leading jet PT, and then we have this theta G or RG, which is scaled by this resolution parameter. So we use this grooming condition, so which is the typical procedure used in the soft drop grooming technique. So this is the results of this RG, which is measured, and you can see this is for the PT interval 10 to 20 GeV on the left hand side, and on the right hand side we have this higher PT interval 20 to 35, and you can see this one for 3 different beta cases, which I was shown on the previous slides, where we are using that soft drop grooming condition. So B equal to 0 is we are using very stringent case, and B equal to infinity, that is a very loose condition on soft grooming. So you can see this distribution, and if you go to the higher PT, there is a sensitivity to that, and you can see this distribution of this RG. So now coming back to this RG distribution, and then trying to study how it behaves when you try to look for this Q hat L, which gives the additional means how this quark propagate into the nucleus is given by this additional Q hat L for different kinematics, and you can see that it shows the broadening, or in this case as well. So we can use this jet substructure studies to study this EA collision at EIC. So again, before going to the next results, I would like to again give some introduction to the things that we will be using. So to calculate this single spin asymmetry or the double spin asymmetry, we start with this measuring the cross section in terms of, say, invariant mass or PT or any other observables, and this is for the unpolarized case that we calculate d sigma, and then based on how the spin of the target, whether it is a transverse or longitudinal, we try to take the difference between this transverse case, and then we try to take in the opposite direction, and then we take the difference to calculate this single spin asymmetry. And similarly, this is for the beam single spin asymmetry when the beam is polarized, and again we take the difference to calculate this ALU. Similarly, we do the double spin asymmetry, where here in this case both target spin as well as the beam spin, they are longitudinally polarized, and we calculate these differential cross sections and take the difference and normalize with the total cross section that we use for the unpolarized case to calculate this double spin asymmetry. So these are the things that you have seen over the time in this conference or workshop. So this is the nucleon polarization, unpolarized, longitudinally polarized, and then transverse polarized. And this is the quark polarization, again unpolarized and longitudinally polarized and transversely polarized. So I will be talking about this Sieverts asymmetry where we have this transverse polarized nucleon. And secondly, I will also talk about this helicity where we have this both nucleon and this quark polarized case. Okay, so I will now talk about this azimuthal correlation between this lepton and jets. So this is, you can see, I think Felix gave a very nice picture, better than this, where it was a longitudinal view, but it's the same picture, okay? And you can see the electron going and the jet going in the opposite direction. So here you can see the initial case where you have this transversely polarized proton colliding with the electron. And then we get those two objects, which is one is electron and the jet. So this results that, so this is from the EIC detector implemented in the using the Delphis, which is used for the smearing effects, and this is the thing that we see in the EIC detector. Okay, so also Felix have talked about this. So we try to measure this QT, which is nothing but the imbalance that we have in the electron and jet PT. And we try to measure that single spin asymmetry as a function of the QT. And you can see that this distribution where there are lots of theory uncertainties. And if you see the projected precision at the EIC, you can see the error bars for different QT region. And if you scale that to 100 femtobarn inverse, we can have a very good precision to do this kind of studies, which will give us this TMD PDF. We can also look at the hadrons inside the jets and see the distribution of hadrons. In particular, the transverse momentum of that hadrons with respect to the jet axis, because that is sensitive to the Collins asymmetry. And we can measure that as well using the hadrons that we see inside the jet. So here you can see again the single spin asymmetry as a function of this fraction of the hadron momentum on this axis. So this is again, you can see calculated for the pions, pi plus and pi minus. And Felix also said that we can see this when you include some charge information, that is, you can see nicely separated region. So this again compare for the different x going from the very low x to high, and there is some sensitivity if you see going from the low x to the high x region. Okay. Next, I would like to talk about this nuclear modification factor in the EA collision. So you can see this, I shown on the first few slides that when the quark enters into the nucleus, it experiences a multiple scattering, and you can see this study showing the REA, which is calculated for jet, as a function of jet PT. And these are the distributions for different cases where they include only the initial effects, which is shown in the blue region. And if you add the final state effects, that is shown in this green. And if you have the full, then you have this distribution shown in this red region. So these are a first calculation of inclusive jet production at EA, or electron gold collision, that they have measured. And these are the results where they have used this NCTEC 15 and results that they got using this full EPPS is shown over here. So there is a suppression that you can see going from this 5 GeV to the 25 GeV that you can see in this. Next, we can look into the gluon helicity distribution inside the proton. And I will introduce the star results first. So this is again the double spin asymmetry for inclusive jets, which is shown in this left-hand side plot. And you can see this double spin asymmetry as a function of this PT scale of the jet. And you can see that there is an increasing asymmetry in this single jet events. And if you try to look at the same thing in this dijet events, you can also see this kind of longitudinal or double spin asymmetry in these events, where there are two cases where you have this, they have separated into the eta 1, eta 2, or sine of eta 1 and sine of eta 2 if they are equal. So you have this one, and then if they are not equal, it is shown over here. And this is, they have calculated this asymmetry as a function of the invariant mass of the dijet. Next, again, trying to study this gluon helicity. And these are some leading order, next to leading order, and next to next leading order results from Oldis. And you can see this is for the single jet and measured as a function of the PT of the jet. And you can see the ratio between this next to next leading order to the leading order, which is the K factor, which is shown over here. And you can see the NNLO does the better job as expected in most of the cases. So this is for, they have measured for the unpolarized case, but the same thing when you include the polarization in one of the beam. So you can see on the bottom plot, it is the polarized case where they again calculated this as a function of PT. So this K factor improves when you have this polarization, which you can see as compared to this. So they also try to calculate this again, double spin asymmetries at same leading order, next to leading, and next to next leading order. And you can see here as a function of PT and as a function of eta. And again, the next to next leading order does the better job. But if you look at this eta distribution, there is a lot of tension between the next to leading order and the next to next leading order results. Okay. Now looking into the dijets and see how that can contribute to the gluon helicity information. And you can see this dijet double spin asymmetry, which is calculated as a function of the invariant mass of dijet. And you can see this for the two different cases, one for the Q-City-Compton scattering, which is shown over here in the blue, and another for the photon-gluon fusion. So this you can clearly see the separation, and you see the sizable asymmetry when you go from 10 GeV to 100 GeV of dijet mass. And if you try to combine this and look at the same results or dijet double spin asymmetry for different Q square interval, then you can see that it also shows sizable asymmetry, and this is for the 100 GeV square to 500 GeV square, very highly virtual case where you see this asymmetry in the dijet mass. Okay, so I think Felix has explained quite in detail about these machine learning techniques to use to identify or classify jets at EIC. So I will go quickly into this. So I will skip some of the part if possible. So, so here you can see we have these two cases, one with the high Q square event where we have this, again, same thing what I was discussing earlier, electron and jet. And for the low Q square, we have this dijet event in this case, where you can have this photoprotection, where you can go to the, you can try to see resolved case and also the direct case of these events. Now trying to separate these flavors. So this is the rock curve, and you can see that when you include the information of the out of jet particles, it does a very good job in separating this up quark and the down quark jet. And on the right hand side, there is this is the distribution where you try to separate this up, down, and strange. So this is the rock curve where you are having this information from the particle flow, and you can see that once you include the particle identification information, you can go up to more than say around 0.85 or something. Okay, so it does a very good job in identifying this jet's flavor. We can also identify the quark and the gluon, and you can see same results for the quark and gluon jet. And we can go further and also try to study and separate the hard processes from this QQ bar, QQ, and gluon. Okay, and you can see the separation between this QQ bar and QQ versus this gluon processes. So this classification or identification of this jet's flavor and the processes can be used to tag the resolved photoproduction processes and other studies. Okay. So this is also another result based on the machine learning from the recent result from the H1 collaboration, where they try to measure this jet imbalance, okay, QT at high Q square. And as I said, that QT is sensitive to the TMD PDFs and so on. So you can see these results, QT, they have measured, okay, and they have compared these results with the NNLO and also the calculation from the TMD. So TMD does a fairly good job in explaining that in the lower QT region, and NNLO does a good job in the higher QT region. And you can see the similar thing when you try to see the azimuthal correlations and trying to compare with this TMD calculation and the NNLO calculation. So these results would serve as a baseline for EIC calculation in future. So from going from EP to EA, so we can always use this as a baseline results. So now talking a little bit about our EPIC detector performance, how well we can measure these jets. So here you can see the jet energy versus jet eta for this is for 63 GeV, and this is for the 141 GeV. So very high limit and the low center of mass energy. And on the right hand side, you can see for the going to the very high Q square region. And you can see they are doing fairly good job in measuring these jets after passing through the detector effects, like so we use the Delphis for simulating or parameterizing the detector related effects. So looking at the jet energy scale and the jet energy resolution as a function of the jet energy. So you can see that is also fairly doing well. And this is again for very high Q square region and for highest center of mass energy. And here the jet resolution parameter is 0.8 that is used. And here again compared for the two different magnetic field resolution parameters, and 1.5 and 3, and they are doing pretty much same. So you don't see much difference if you use those two different parameters. So yeah, so we can understand our jets very well, and the jet energy scale and the resolution is pretty good, which to do our measurements for a different like lepton plus jet Sieverts asymmetry or the dijet PT balance and so on, all the results that we can do with this. So now let me go to the heavy flavor quickly. So here again we can see that the dicham D0 or dicham jets are sensitive to the again Sieverts asymmetry, and you can see here the single spin asymmetry as a function of this azimuthal difference between this D0 or these two jets from the D meson, and you can see the projections of these results, how that will behave, and how well we can calculate this Sieverts asymmetry in EIC. So these error bars are shown by projecting these results to I think 10 femtobarn inverse data, and we have a very good our systematics are under control, and we can do this measurement. Again, looking at the similar thing that we have looked for the jets, but we also see this single spin asymmetry for the D mesons or the heavy mesons as well. So you can see this looking at the hadron fraction, and again you can see the projection or the accuracy or precision that we can attain at the EIC, and we have a very good precision control if we collect the 100 femtobarn inverse of data and do this calculation. Okay. Now going to the exclusive production of upsilon, and you can see in this left-hand side plot for the EP collision. So this upsilon goes into E plus E minus, and you can see that it is nicely separated, and we have this excellent PID performance. So this was measured for during the Athena proposal, and you can do this upsilon measurement for both electron and muon decay pair. And on the right hand side, you can see the total cross section for the as a function of this proton or the gamma p center of mass energy, and you can see it is nicely increases with this W. And inside this, you can see the differential cross section as a function of this minus T mean, and it is compared again with the different Monte Carlo from the E starlight and the Lager, and again this is passed through the our Delphis or the detector simulation, and these are from the APIC collaboration results. Okay, so yes, so we can use this excellent PID performance, and we can measure this epsilon production. Moreover, we can also try to measure this invariant mass spectrum of various other D mesons and the B mesons. So here you can see the reconstructed D mesons, okay, and on the middle you have this B plus B minus, and on the right hand side you can see the jet PT spectrum for the different jets. For example, bottom jet, charm jet, and the light quark jets. And these are for the different scale, and this is again scale to the 10 femtobarn inverse of the data. And you can see we have again very good control over our systematics, and we have better particle identification to measure these heavy flavors. We can also try to measure this nuclear modification factor, REA, for d mesons, and you can see this is for the different repetitive interval, -2 to 0, in between, and then 0 to 2, and then going to the forward region. And you can see this is again compared or shown the different systematics as well as the statistical uncertainties on the projected luminosities or the scale luminosities, and we are still under control. So we can measure this d meson nuclear REA in this case in better way. Okay, so finally, so this is again looking at the dijets and measuring the dijets imbalance, and you can see this is for the again projection for the EP case, which is shown in the black points, and the red points are for the EA case. And again, this is the projection for EP case, it is for the 10 femtobarn inverse, and for the EA case, it is about 500 picobarn inverse. So the error bars are pretty much under control, and this is again passed through the detector simulation. So yes, so we can nicely measure the dijets as well. Okay, so this brings me to the summary, and as I said, jet measurement at EIC will contribute to nearly almost all the aspects of the EIC goals that we are looking for. And in near future, as the development in the jet clustering or jet substructure measurement tools improves, along with the machine learning techniques which can classify partons, hard processes, or even correct the detector effects as H1 did using Omni, we can have a much more new opportunities in jet physics at EIC. And of course, heavy flavor measurements at EIC will also explore both initial and the final state effect with better precision. So thank you.
Thank you, Prabhakar, for your talk. Questions for Prabhakar?
I missed your point in the previous slide when you talk about heavy quark transport coefficient. So what precisely would you like to measure? The diffusion coefficient of the heavy quark, or what is it?
You're talking about Q height you are talking about, right? In this case, or even
for the heavy quark also you are measuring the Q height?
Yeah, for heavy quark also you can do that.
But is it related to the momentum diffusion coefficient there?
I don't have details about that, Okay. But you can go to the reference, that I have here.
Okay, any other questions?
Thanks. I have a quick question about the end of your talk. You had these projections for EP and EA. What goes in? Is it just different luminosities, or is there anything else that goes into these projections?
Which one you are talking about?
Right at the very end of the talk. One more. Right, there you have like EP and EA. Is there anything else different for these projections, or is it just different luminosities for EP?
Yeah, you just pass through the simulation as far as I understand, and then you just scale the luminosities and then try to calculate the error bars.
But you're simulating also an EA.
Yeah, you're simulating,
I see, that goes into the uncertainties. I see, okay, thanks.
Okay, if there are no other questions, let's thank Prabhakar again.